Imagine I am running a LoadRunner test against an application where the traffic goes through a load balancer and then to the four application servers. For this example, I am using this simplified architecture. At around 1000 virtual users, everything looks normal. But when the load reaches around 1500 virtual users, response time starts increasing. Now the interviewer tells me the load generator is healthy, load balancer CPU is normal, load balancer memory is also normal, and there is no APM tool available. Then comes the question: how would you determine whether the load balancer is contributing to the performance problem? I would not immediately say that the load balancer is healthy just because CPU and memory are normal. Instead, I would investigate how the load balancer is behaving. And remember, no APM doesn't mean no monitoring. We can still use the load balancer native statistics, configuration, logs, operating system monitoring wherever applicable, and load runner results. So let's investigate this step by step. My first question is the load balancer distributing the traffic properly? So I start by checking how the requests are being distributed across the four application servers. I look at the metrics such as requests per second, active connections, and other backend statistics available on the load balancer. Suppose I see app 1 is 20%, app 2 is 20%, app 3 is 18%, but app 4 is 42%. Now, this immediately gets my attention. App 4 is receiving much more traffic than the other servers. But I do not want to jump to the conclusion that load balancer is the bottleneck here. There could be a valid reason for this uneven distribution. So my next question is, why is app 4 receiving 42% of the traffic? To answer that, I first check the load balancing algorithm and configuration. Now I check the load balancing algorithm. It could be round robin, weighted round robin, least connections, or another algorithm depending on the load balancer. If weights are being used, I also check the backend weights. Then I compare two things: what should happen based on the configuration and what is actually happening. An uneven distribution is not always a problem. It could be the expected behavior of the configured algorithm. But in our case, the configuration does not explain why app 4 is receiving 42% of the backend requests while app 1 is receiving only 20%. So now I have another possibility to investigate. Could session persistence be causing more traffic to go to app 4? That's what I'll check next. Now I investigate session persistence, also called sticky sessions or session affinity. First, I check whether the persistence is enabled. Then I check what type of persistence is configured, what key is being used, and how long the session remains tied to a particular server. This is important in performance testing because session persistence can affect how LoadRunner users distribute across the application servers. For example, if persistence is based on source IP and many test users come through the same source IP or a small number of IPs, many sessions could end up being routed to the same server. In our case, the evidence shows that more test sessions are being associated with app 4. This could explain why app 4 is receiving around 42% of the backend requests. But I don't want to conclude it. I need to rule out the other possible reasons for the uneven distribution. So next I will check backend health. Now I check whether all the four application servers are healthy and available in the load balancer pool. I look at the load balancer's health check information and verify, are all four servers healthy? Has any server been removed from the pool? Are there any health check failures? For example, if app 3 was unhealthy and removed from the pool, the remaining servers would naturally receive more traffic. That could explain the uneven distribution without the load balancer being the problem. But in our scenario, all four servers are healthy and participating in the pool. So backend health does not explain why app 4 is receiving 42% of traffic. Now I'll check another important area: connection behavior. Here I want to make one important distinction. Requests are not the same as connections. Because of Keep Alive, multiple requests can use the same TCP connection. So I check a few key things here. Active connections, new connections per second, connection failures, and connection reuse. I also check whether the load balancer has any relevant connection limits. If it's a Linux based load balancer, I can use commands such as ss-s to get a summary of socket statistics and ss-tan to inspect TCP socket and connection states. If it's running on Windows, I can use relevance performance monitor counters based on the load balancer implementation. These OS level metrics provide supporting evidence, while the load balancer's own statistics remain an important source of information. In our scenario, the connection metrics are within normal limits. There are no unusual connection failures, and I don't see any sign of connection exhaustion. So, connection behavior does not appear to be the cause. Now, I will check some other load balancer specific possibilities here. At this stage, I also check for a few load balancer specific issues. For example, connection limits, NAT or SNAT limits if applicable, retries and timeouts, and queue or backlog information if the load balancer provides it. If there are multiple load balancer nodes, I also check whether one node is handling much more traffic than the others. The exact check depends on the load balancer product and the architecture. Without APM, I can get this information from the load balancer's native statistics, logs, and configuration. If it's a software load balancer, I can use relevant Windows or Linux monitoring. In our scenario, none of these checks show a load balancer capacity problem. So now it's time to correlate these findings with the LoadRunner results. Now I bring the LoadRunner into the investigation. I look at the relationship between vusers, transaction rate, response time, errors, and throughput. Here, what I see. Up to around 1000 virtual users, response time is stable. As the load approaches 1500 users, response time starts increasing. At around the same point, App4 starts receiving a much more higher percentage of the backend requests, and its response time also starts increasing. Meanwhile, the other application servers remain relatively stable. So now I can see a clear pattern. Load increases, more sessions are routed to the app4, app4 receives more requests, app4 response time increases, and overall response time increases. The load balancer CPU and memory are still normal. All four application servers are healthy. The configured algorithm does not explain the traffic imbalance, and the session persistence behavior appears to be concentrating more sessions on app4. The interviewer asks, how do you know app4 is the problem? Couldn't app4 simply be slow? That's a very good question. I wouldn't say app4 has high traffic, so that's the root cause. That's not enough. Instead, I explain the evidence I have collected. First, LoadRunner shows exactly when the response time starts increasing. Second, load balancer CPU and memory are normal. Third, I find an unusual traffic distribution. Fourth, the load balancing configuration does not explain this imbalance. Fifth, the session persistence data shows that more sessions are being routed to app4. Sixth, all four application servers are healthy. And finally, the connection checks don't show any load balancer capacity issue. Most importantly, app4's workload and response time increase at the same point where the overall response time increases. So the evidence strongly points to app4 becoming the hotspot because of the uneven session distribution. But I still need to prove that this is the root cause. That comes with the fix and retest. Based on the evidence so far, my root cause hypothesis is session persistence is causing the performance test workload to be distributed unevenly. As a result, App4 is receiving around 42% of the backend request, while App1 is receiving only 20%. This makes App4 the hotspot. As the workload on App4 increases, its response time also increases, which contributes to the increase in overall application response time. So there are two important things to distinguish. The immediate bottleneck is app 4. The suspected root cause is the session persistence behavior causing the uneven traffic distribution. But I don't want to stop at a hypothesis. The next step is to make the appropriate configuration change, run a comparable load runner test, and prove whether the performance improves. Now comes the most important part, prove the fix. I wouldn't blindly disable session persistence because the application may require it. First, I understand the application's requirement and then decide whether to remove, tune, or modify the persistence configuration. Before the change, the traffic distribution was something like this. So, App 4 clearly receiving a much larger share of the traffic here. After the corrective action, the traffic becomes much more balanced. But balanced traffic alone doesn't prove that the problem is fixed. So I run a comparable LoadRunner test again and compare backend traffic distribution, App4 response time, overall response time, transaction performance, and errors. If the App4 hotspot disappears and the previous response time degradation is also resolved, I now have a strong evidence that the corrective action addressed the problem. That's the difference between I changed something and performance improved, and I identified a likely cause, made the appropriate change, and proved the result with a comparable test. That's proper performance engineering thinking. So let's answer the original interview question one final time. Response time increased, load balancer CPU and memory are normal, and there is no APM tool. How would you investigate? My approach would be first I use LoadRunner to identify exactly when the response time starts increasing. Then I check the load balancer's backend traffic distribution. In our case, I found this kind of distribution. Next, I check the load balancing algorithm and backend configuration. The configuration doesn't explain this imbalance. Then I investigate session persistence and find that more performance test sessions are being associated with App4. I also verify that all four backend servers are healthy. Then I check connection behavior and other relevant load balancer limits. I don't find any evidence of a load balancer capacity problem. Finally, I correlate these findings with the load runner results. The pattern is clear. Load increases, more traffic goes to App4 response time increases, overall response time increases. So my root cause hypothesis is session persistence is causing an uneven distribution of the performance test workload, making App4 the hotspot. I then make the appropriate configuration change and run a comparable load runner test again. If the traffic becomes more balanced, App4's response time improves, and the overall performance problem is resolved, I have a strong evidence that the session persistence behavior was the root cause. That's how I would investigate a load balancer performance problem in a real performance testing interview.